And in a similar way, I think you have this double summation equation. And of course, the B-spline surface follows from the same principle that we saw. But what will be the similar idea in terms of, remember in the convexal all property also remains the same. So this, except that this is a completely 3D convexal that you are looking at control net. Okay, so the entire Bezier surface will lie within the convexal of the entire control polygon points or control net points. Okay, and that holds good for surface also. Guys, are you there? So what would be a similar case for B-spline surface? What was the similar analogy for B-spline curve in terms of convex hull? No sound.
We have a B-spline, say like a volume or solid instead of a
No, but I'm talking about the analogy of the convex hull for the B-spline. What is the
So
analogy for the
we had a variable called order.
We had order K. So remember, if you recall, it is K successive convex hulls. We have to look at it. So the curve will lie within the convex hull of each of the K control points. Okay, the K is an order which we saw. It can go from 2 to n plus 1. Okay, I'm just recollecting that. So when K becomes n plus 1, what was the curve that we had? The B-spline reduced to a
Bezier curve, sir.
B-spline reduced to a Bezier curve. Now, what are all those two here? Instead of order K, what we will have? We will have an order K in one direction, which is the U direction, and then the order L. I think that's what we had notated. So you can see there is a K here, and then there is an L here. So if you look at this equation, there is a K and there is an L. So suppose if your control net is like this, let us say you may have control net like this, whatever, right? Let's say you have a control net like this. So suppose say if A equals 2 and also L equals 2, what does that mean?
Sir, then the curve,
Bezier.
we will have to look at consecutive
consecutive 2 by 2. So that means you have to look at this guy, right? And then the curve has to lie within this patch. That means that remember this is 2 here on this side, 2 here on that side. And from here, you have to look at 2 here and 2 here. That means what? You have to look at this, this patch, this control net. And so to speak, you are going to keep on doing it for 2 by 2, right? So this will, so what will happen to the surface now? So when you have K equals 2 and L equals 2, what will happen to the surface now? What will be the surface you will be getting?
Degree 1 surface in one direction. Actually, both of them are 2, so degree 1 in both of them.
Correct, but what will be the output? You have this control net. What will be the surface now?
Plane surface?
So it will be a collection of all the control nets.
So you get the entire control net as your B-spline surface. Suppose I have a control net like this. Okay, this is in 2D, so it's like little easier. Okay, suppose if I draw a control net like this. Okay, let us say on both directions we have 4. So if you have so you can see it will go like this. So this is the control net. So what will be the B-spline surface for this guy? If you have K equals 2 and N equals 2.
So the whole, each portion of the control net will be considered.
Which portion is a patch. Okay, so the entire control net itself will be the surface for K equals 2 and L equals 2. Suppose if you increase this to K equals, say you have, okay, I have so many here. Suppose say you have, in the top picture I have flattened this thing. So suppose if you have K equals 3 and L equals 2, what will happen? So how you should look? So you have to look at 3 guys in this direction and then 2 in this direction. So you can see that your surface has to lie within this convex hull in the first one. This will be one patch. And then this other patch will be coming from here. This is the other patch. And then you have to move. Remember k equals
3,3, right?
So this is so you have to look at these sub patches on that. So you have to go to the next consecutive 3 by 2. Next consecutive 3 by 2 is this guy. Correct? Oh,
Yes,
sorry.
sir.
So
Sir,
this is
how is it 3 by 2?
3,0.
Because
Sorry, I
this
should have
is
3 by 2. Correct. So this is a 3 by 2 guy. Okay. So the 3 by 2 is only one guy. So then that means you have another 3 by 2 here and one more 3 by 2 here. So the successive
sir-
3 by 2s. Correct?
But
So
sir,
if-
we are considering k is equals to 3 and l is equals to 2.
Correct,
So
correct.
we need 2 by 1 patch, right?
2 by
yes, sir, I
1,
thought
2
the same
by
thing.
1 will be the degree of the curve in either direction. But it is only 3 by 2 you have to take in terms of points from the control net.
Yes, sir. So if we take 3 points, then these 2 squares are considered.
So if you, okay, let me draw again. Suppose if you have k equals 3 and l equals 2, that means you have to take 3 points at u direction and l is 2 points in the u direction. So what will happen to the control sub-control net? So this will be the control net for the first patch.
No,
Correct.
sir. It should be one less,
Sir, I'm
right?
still a bit confused. Would it
It
not
is
be a 2
taking
cross
4
1?
points.
No, see, okay. Oh, okay, 1, 2, 3. That previous picture was correct in that case. Correct. So if you remember in 2D, when you had this thing, you have to take 2 consecutive control points and k equals 2. So remember when k equals 3, you have to take 3 consecutive points here and then 2 consecutive points on L. So that means this will be the paths that you are looking at. And similarly, this will be the paths and you keep on going for each of them. You're right. Then again 2 here and 3 here. So this will be the paths and this will be the paths. So if you go for a 3 by 3, then you will have a different set of subpatches. So if you have 3 by 3, but remember the degree of the curve will be 2 by 2. So then this patch will be 3 by 3. So you have to have these 3 patches, 3 control points on either side, and this will be the other patch on that. And then you have to up it, and then this will be 1. Is that right, or is there anything wrong?
Yes, sir.
You are going
Yes,
to
sir,
move
I
only
think that's correct.
2 in the right side and 3 on the other side on. But consecutive, remember when we did this thing, first we did these 2 and then again we did the other, this point, again we started and then again we started. So we had to use the previous point also to, it's like a k consecutive points, okay, one from the other. So in a similar way, when you move the patch, there will be an overlapping patches in your surface, but not on the actual Bezier surface. It will be only in the case of your convexal. You can see there is a patch that will actually come from there. So in some cases it could be independent. Okay, so we have to look at it from that perspective, whether we are going to have a overlapping surface. We don't have an overlapping in terms of parameterization. We may have overlap in the convexal area. We saw it in that 2D also. There will be overlap in the convexal area. Remember that? Did you guys remember that we saw some of the convexal is overlap, but the curve will not overlap?
Yes,
Isn't
sir.
it?
Yes.
Yes,
So
sir.
similarly here, the convexal may overlap of these individual control net, but the surface will not overlap. They will have a clear-cut distinction on the parameterization. That is the idea. Okay, I think more than that, we may be little bit too much. So I'll just show some, I think I have some pictures on that. So these are all some pictures from the book. And you can see how these control net, you can generate locally flat surfaces, which is, I think, impossible if you use any other representation. Like you can see this surface is locally flat here. You can see this portion is a locally flat surface. All the other portions you have curvature. See, these and all you have curvatures, but this also you have curvature. Only in the middle you can see there is a flat patch that is coming. Okay, which I think if you want to design your car bonnet or something like that, you can go with some cranky design by actually suitably placing the control net. And you can remember in the last case, I told if you repeat the control points, you can push your control point closer to that. Similarly, I can one of the control net, I can repeat it and I can make the surface to push towards that control points. All those things, whatever we saw in 2D, are all applicable for B-spline surface also. Okay, so same mathematics holds good, same conceptual understanding holds good, and in a similar way, you remember we saw rational B-spline. That's also we have rational B-spline surface. Then we have saw what are called NURBS, non-uniform rational B-spline surface. We saw in the case of a curve, and this is extended to surface also. So whatever the thing that we saw for 2D curves, it's actually it's a 2D curve. For curves, it is same applicable for the NURB surface also, or the surface. So we have NURB surface, we have rational B-spline surface, we have non-uniform rational B-spline surface. Whatever combination you do, you still have those kinds of surfaces. Okay, so that is very important on that. So you can design very cranky surfaces based on your whatever we have. With the understanding of how do you place your control polygon points or control net points, you can actually design some great surfaces on them. Okay, so any questions here? I mean, the same concept that we saw in the curve, I just extended to surfaces without going too much into the details of the math and so on. But whatever we discuss in the morning, same thing holds good for surfaces also. So maybe I'll just switch to the GUI read on that. So I'll just stop sharing. But remember, it's like a little bit too much to discuss in detail the B-spline surface. But whatever we did, it's applicable. So I will show you some more fascinating things that we can do. I'll switch to the other one. Okay, I'll try to do as much as possible because sometimes it doesn't work the way that I want it because I'm kind of using too many different systems. Okay, so we saw this doubly ruled surface here. Okay, let me just go back to the curve a little bit so that you guys can recollect the curves on the B-spline side. None of the front view and all not working. Okay, I'll show you this B-spline again. So if you recollect the B-spline curve, so as we draw a B-spline, we saw, so we can change the order. So we 3 and then we can 2, we get the same control polygon itself as the curve. And when you increase the order, you see different curves. Okay, this we saw in the morning. But what I would like to show is that, and ask you a question. Okay, now let me try something different. So are you seeing that I'm kind of generating some collinear points in the middle? And what happens in the curve there? So you can see here, there are, okay, this point also I can push a little bit. So you can see that what happens here. Let me add the points again. So what is happening in this particular case? So remember, I'm adding a lot of control points in the collinear direction. Okay, and then I'm going to move out of collinearity. So what is that you can observe now? So what is that you can observe for the curve? So here you can see the set of collinear points. How is the behavior of the curve? You take a close look at these points. So what do you think locally in the curve that happened? Any thoughts on that?
So,
Closely tracked.
So
in the points that are collinear, it's the curve is also flat.
Why the curve is flat there? Because
Because
of
it
what? So why it become flat there? What does it tell you, and what property tells you that it's going to be flat there?
Uh, do we have like control points over there?
So
because here I think you have chosen k equals 4. So there are 4 collinear points over there.
correct.
So in that patch, it will be
yeah, so you can see that like I can draw a curve, but with some straight line in the middle of the curve, right? That's what it sounds, isn't it?
Yes.
Look, can you generate such a curve using any other representation? Like you have so many equations, explicit, implicit form, cubic spline. So can you think of generating such a curve with a straight line in the middle using any representation that you can think of? Is it possible? Suppose if I go to k equals 3, you can see that straight line portion increases, because you'll have 3 in tandem. So there is 1 3 here and another 3 there. So you'll see that increase in the straight. So is it possible such a curve can be generated using any other mode of representation or any other equation that you can think of?
so it might be possible, but we cannot control it as per our demand.
Correct. So you may think of piecing together one straight line with a parabola, and then on another side of the straight line you can fix another cubic spline kind of thing. But each one is its own piece. You don't have a unique representation. Correct. You don't have a unique equation or something like that. So as far as I can think of, generating such a curve or a surface, I think it is only possible using a B-spline surface. I think maybe other experts can probably think of it, whether it is possible to generate such a curve with straight line portion in between using any other representation. Maybe if you take an odd curve like y equals x cube, or maybe x power 5 or x power 7, there will be some. I don't think there will be any big portion of straight line coming in between. Actually, I'm not able to think of it. Okay. So you can see that Bezier B-spline gives such a big facility in terms of generating surfaces. Here I showed only curve, but you can go for surface also. Let me try this surface thing, which I had a little bit hard time, but let me try that. Thing is behaving erratically. Okay, let me just try that. Okay, so what I'm going to do is to show some Bezier surface. Let's see if whether it can do something on that. So you watch out carefully. This U length is 2 and V length is 2 here. I'm going to maybe increase this to 4 possibly. Okay, and then I'll try to give some idea of, okay, 4 means, okay, 1. So I'm going to repeat this again. Okay, so you can see this is a Bezier surface, but all on the same plane. So I'm going to elevate this guy a little bit. Maybe 0.8 or whatever. So you can see a Bezier surface here with how many control points here in this particular case? Are you guys seeing my picture here? Exactly going the opposite of what I wrote it. So are you guys seeing this? What is the control net size here?
So 7,
8, sir.
8. Okay.
Okay, it is basically 4 in one direction and 2 in other direction. So 4 by 2, you can see it becomes a very easy one, right? You don't have to, but we can just, operate on this. Let's say I make this, even if you change one, let's say you change one of the coordinates in the middle point, okay, instead of this -5, say we'll go to -1. Okay, let's see. So you can see that the surface looks very different now, correct? So by knowing how to control these kind of control points, you can actually generate a very different surface. Okay, in a B-spline, it is even more control is even better. But you can see in the Bezier also, we can create some nice surfaces by changing all these points. Okay, so I mean, you can go to any level. You can go to 1 here, maybe 2. So you can create all kinds. So this is how you generate your like a car hood or your fancy car surfaces that you see here, right? In design, you can see how you can create all kinds of surfaces that will. You can probably they try and create more number of control points. Let me try to show that. Okay, so I'm just trying to see how to operate this.
Sir, is there a better software that allows us to model
Actually,
surfaces
I
like this?
see you have Katia and other things which are all monumentally expensive. This is a open source free, okay? So obviously it has only the basic level of thing, but there are sophisticated softwares like Katia. Okay, Katia is particularly used for aerospace, automotive applications. Basically using your B-spline, NURBS, and Bezier. But I think it is quite expensive on that. So it may be too much to acquire that. Of course, if you have a lot of money, you could try to do that. But I go with more with open source, and obviously it's little limited in terms of how we process this. And I also actually, honestly, I don't know exactly how to operate this thing. So that is another problem that I have. But I'm just trying to do that. So U is 4, I use 5. Yeah? Okay. That's a problem. I'll reduce it to 4. Okay, so you got some surface which actually is not a surface because everything is flat here. So we have to elevate some of the local guys like these intermediate points. We can elevate, or we can elevate any of the other points also. So we elevate some Z guys. Okay, so you can see that the surface quickly jumps up, and then we can do any kind of thing on that. So you can see little bit now. So you can see, half the surface on a plane and half of them it is jumped up. Okay. I don't think you can create such surface using other representations. I mean, you can play with that, increase the control points, and you can definitely get better surfaces. So let me try to jack up some of the other 1, 2, 3, 4, 1. Okay, here. So you can create some nice cranky surfaces by just, elevating. You can elevate everything on the Z, and you can see, you can come up with any kinds of design. I mean, this is very limited, and more importantly, I don't know how to operate this clearly. But if you can figure out the way to do that better, I think you can see you can create all kinds of surfaces. So now the thing that you can elevate one or go down the other. Let's say you go make it the third guy go low. Let's say you put this guy 0.2. So you can see the all kinds of surfaces. You can get a flat locally. You can see that this region is a different curvature and this region is a D. So I think some kind of design like this, I think it will be difficult to do in other kinds of other forms of surface representation. I mean, honestly, I don't know, but so you can play with these locations of these points, and unfortunately mouse control is not working very well there. And then of course you can go to order. If you go to order 2, you can see this is how the surface looks. Okay, one is order 3, another is order 2, and then you can reduce the order there also, and then this is how the surface will be. So on the same representation, you can actually see how many different kinds of interesting designs you can come up with. So I don't think such things are kind of possible in other surface representation. Maybe other guys can comment on that, but you can see just by clicking the change in the order, you can get a different surface on that, which I think it's almost impossible to have this kind of control in any other form of equation. So you just play with it and then try to understand different kinds of surfaces. This is what I saw is very primitive demonstration. Okay, largely due to that I don't have all the icons here, and then I'm having difficulty because of the varying in operating systems and so on. So you guys, if you are on Windows, you should be able to see a lot more other icons. And I would also suggest you take a look at the YouTube video that I had posted. This is done by Gershon Elber. This is kind of his own brainchild. Okay, and as far as I can see, he is the creator of this. Of course, it's a lot of support from a lot of students and postdocs and so on. But the entire software, which is called ERIT, and this GUIRIT is a graphical user interface for the ERIT. Okay, so ERIT is a big program by itself. I think I wanted to run the demo. Unfortunately, that's not working very well. But this is it about, I would say, about B-spline curves and surfaces, and the subset is the Bezier curves and surfaces. So maybe I'll little bit stop here on that. So any doubts, any questions you have?
Sir, is the cubic spline method that we studied like a special case of B spline where k equals 4?
You can arrive at the control points. For example, you can equate this bicubic or a cubic B-spline, okay, and then you can equate your cubic spline equation, and then you can find an equivalent control points for the spline curve, cubic spline curve that you have. So that is possible.
Okay, sir.
Okay, it is definitely possible that you can do that. Maybe I'll show some other demo on that. So, like for example, you can also look at maybe here. Some of them are not appearing here. So there are so many utilities. I think some of them I'm not able to see here. Okay, let's say I go to this. Okay, hopefully this works. So I'll just take this helix. Okay, you can see that there is a helix here, and I can change the pitch. So you can see that a helix of different pitch appears here. Okay, and then I can just using the evaluation, you can, the tangent, right? So if you want to run a tangent, okay, I forgot to apply that. So this is a curve that you have, and if you want to evaluate with the tangent, that you can tangent or curvature. So you can see there's a tangent line appearing. You see a red mark and then this yellow mark. Basically, if you change the parameter, that means it's going to different positions of the curve, and then you can see the tangent also varies on that. So you can see the tangent is varying. Are you able to see that?
Yes, sir.
So as I move it, you can see the way at various locations of the parameter values, you can see the tangent goes then. So you can see a tangent. So you can also do the normal. So if you go here, you just do all that and it does the normal at the. So you can see the normal appears here in that. And if you change the parameter value, then see that normal also goes. So this is normal, you mean, I don't know whether you guys have studied tangent normal. Have you studied binormal any chance? Do you know binormal?
No, sir.
Sir, is it like in 3D you have two normals in like two
Yeah, so
directions?
maybe I'll briefly talk about it. So in okay, I'll just show that picture. Okay, so if so, I have to share the other screen now. Let me go there. Or of course, I have something here itself. So if you see this, okay. Okay, so if you have a curve like this, right? So you can see that this alpha dash is basically the tangent at a point on the curve. Are you able to see this mouse movement? Can you guys give me some feedback?
Sir, the
So I
mouse
can't see
is
the
not
mouse, sir.
Okay, you
is not
see that there is
visible.
an alpha dash. So alpha dash basically amounts to tangent at that point.
Yes,
Yes, sir.
Okay, now you see a perpendicular one to alpha dash, which is alpha double dash. This alpha double dash basically will be along the so-called principal normal. Suppose if you have a space curve, right, like a helical curve, and if you have a normal plane, that means if we take a plane at a point which is perpendicular to it, you can find several normals. Yes or no? Because if you have an entire plane which is perpendicular to tangent, which is a space curve, you can see lot of normals on that. So there will be
Yes, sir.
one normal, right? There will be one normal which coincides with the circle of curvature there, which will coincide along the circle of curvature. That normal is called as principal normal. So this alpha double dash actually coincides with what is called as principal normal. So these alpha double dash, which is basically a curvature, and then it coincides with the normal. So you have the alpha dash, then that is the tangent t. You have the normal, that is the n. If you take the cross product between t and n, okay, tangent and normal, then you get what is called as a binormal. Okay, so now you can see this picture. So there is a tangent here, there is a normal, and the cross product between tangent and normal, you see the vector b. So this vector b basically is called as the binormal. Okay, that is between tangent and normal. When you take the cross product between tangent and normal, you will get what is called as binormal. So this T, N and V are supposedly form what is called as a Frenet frame. I mean, we don't want to go too much details. So from the differential geometry, you can see that this completely defines the curve, which is a little bit too much of a statement. But you can see as you move this T, N and V along the curve, this completely defines the curve. That is the idea of using the tangent normal and binormal. It is similar to your XYZ coordinates, like your frame of reference. T, N and V also forms a frame of reference. This is called as tangent normal and binormal. That's something called as a Frenet frame. Okay. A similar concept holds good for surface also. Is that okay? T, N and B. Tangent T, N is normal and binormal is a cross product of T and N. Okay, so that is what you can probably see here. I don't know whether binormal is going to come. Okay, let me put this. Oh, okay, let's see. Let's use the word. Okay, I'm not sure what does that actually mean. Okay, possibly it's okay. You can see that this is showing this picture, and you can see as it goes. It is the, I assume it is the cross product between a tangent and a normal, and you see those big directions, which is a binormal. I don't know what it is your by tangent. I'm a little confused. Okay, so this is applicable only on a space curve. Okay, so by binormal and so on. So this forms what is called as a Frenet frame of reference, like your XYZ Cartesian frame. You have a frame called Tn and V. So this is this of course goes beyond what I have discussed now. So similarly in the surface also we have what is called as a curvature. So this is a tangent plane. So you can see at a point there will be a tangent plane, and then you have two tangent vectors in two different directions, u and v, right? It will be u direction x dou x by dou u, and then this is a representation of x of u comma v. Okay, all the notations are mangled up because of different books. Okay, so you have to be a little bit patient. So if you do that, this is where somebody asked about a Jacobian.
yes,
Correct.
sir.
Who asked about Jacobian? So Jacobian comes here because you have dou x by dou u, dou x by dou v, and so on. Okay, so here you'll have the Jacobian will come in, but then this will become a tangent plane consisting of these two vectors in the one in the u direction and one in the v direction. So this cross product between these two tangent vectors generate what is called as a normal. Okay, so let me skip this thing, it will be too much. So you can see that this is a normal. Okay, so this normal comes out of this point, which is this is a tangent vector in the u direction, tangent vector in the v direction. If you take a cross product, you will get a normal direction for a point on the surface. Guys, are you there?
Yes, sir.
Okay, now now if you look at all these, okay, so you can take similarly that we described the ruled surface process. So you can take a plane that contains the normal, okay, and then you can see there is an intersection curve. Are you guys seeing this intersection curve?
Yes, sir.
Yes,
So
sir. But that is not parallel.
that that is what do you mean parallel?
As in, that is
Parallel
not
to the
parallel to
direction
either.
of Okay,
Yes.
need not be, but still it will generate a curve, correct?
Yes.
So this curve will have a curvature at that point P. And
Yes.
if you rotate this plane about that normal, you will have several such curves, isn't it?
Yes.
If you rotate this plane about this line NP, you will have several curves like that, isn't it? Each curve will have a curvature on its own. Yes or no?
Yes.
Yes, sir.
Yes. Yes.
Okay, now you find the maximal curvature out of it and the minimal curvature out of it. Then they are called as principal curvatures.